Hey guys, this video is going to be about the singular value decomposition. Um, well, let's just get started. Let's say we have an M by N matrix. Okay. Um, okay, and let's take Q to be, the minimum of M and N. So like for example, if A is a 15 by 3 matrix, Q would be 3. Now the rank of A, let's call that R. So R is going to be less than or equal to Q. That's the number of linearly independent columns or the number of linearly independent rows, whatever. Okay, the rank of A is R. And now let's look at A star A. That is a N by N matrix. And in fact, you can show that A star A is positive semi-definite, so we know it has a square root by assignment 4. Okay, and we'll just call the positive eigenvalues of A star A to the 1/2. We'll call those positive eigenvalues sigma 1 is the biggest, and then that's bigger than sigma 2, greater than or equal to sigma r, and those are all positive. Okay. And then we define the singular values of A to be, well, those positive eigenvalues of A star A to the 1/2, and then followed by the remainder up to sigma r plus 1 to sigma q are just going to be zeros. Okay, and the singular values of the zero matrix are just going to be all zeros. Okay. Okay, and then so this is fine. This is just a definition though. We just want to write down a theorem that says some of the basic properties of the singular values, and then later we want to say like how it can decompose a matrix in terms of its singular values. So first let's just say some basic things about the singular values. So A, again, an M by N matrix. R is the rank of A. Q is the minimum of M and N. So we know that R is less than or equal to Q, and Q is less than or equal to both M and N. Okay, now sigma 1 up to sigma q are going to be the singular values of A, and C is just going to be a complex number. Okay, now the positive eigenvalues of A star A and AA star are going to be the squares of the singular values. Okay, meaning that the rest of the eigenvalues of both A star A and AA star are all zeros, even though that, like a different number of zeros. Okay, the sum of the squares of the singular values is going to be the trace of AA star, and also that's going to be the trace of A star A. Okay. So this has some kind of significance in terms of the size of the entries of A, which we won't get into right now. Okay. Furthermore, if you look at the four matrices, A star, A transpose, and A conjugate, they all have the same singular values. Okay, and if I multiply A by a scalar, the singular values of CA, well, it just has the effect of multiplying each singular value by the modulus of C. So C is a complex number, so we multiply it by its modulus. Okay. And we're not really going to prove this. Okay. So that's some basic properties of singular values, but the main theorem we want to show is that starting from knowledge of the singular values, we can find a factorization for A. So this is called the singular value decomposition. Okay, so this theorem is basically telling us that a singular value decomposition exists. So first, let's take A to be a non-zero M by N matrix. R is going to be the rank of A, and then we find the positive singular values of A. call them, there's R of them, so we call them sigma 1 down to sigma R in decreasing order. Okay, and then we define a diagonal matrix, an R by R diagonal matrix, to be just the singular values on the diagonal. Then under this assumption, there is an M by M unitary matrix V and an N by N unitary matrix W, such that A is V times sigma times W star, and this sigma is kind of a block matrix. In the top left, we have the singular values going along the diagonal, and then the rest of the blocks we have all zeros. And it just, like, to define sigma, I just have to tell you how many, like, what are the dimensions. So so this block matrix is divided up into R rows and then M minus R rows and R columns followed by N minus R columns. So sigma is an M rows and an M by N matrix. That's what sigma is. And so if we just like say V is an M by M, sigma is an M by N, and W star is an N by N. So we have M by M times M by N times N by N is an M by N. So this kind of, at least it makes sense that we can multiply these things together. Okay. And I wanted to give you a little idea of how to prove it, at least. And then after we discuss the proof, I just want to give you like a made up kind of toy example. Okay, let's try and prove it. First, we can assume that M is greater than or equal to N. If N is less than M, then just prove the theorem first for A star, which is the conjugate transpose. And then once you prove the theorem for A star, take the conjugate transpose of the whole thing you just proved, and you get the theorem for A. Okay, so it's safe to just prove this theorem when there's more rows than columns. Okay, so now we have M rows and N columns. Let's work out what is A star A. A star A is a matrix whose conjugate transpose is equal to itself, and so it is unitarily diagonalizable and all its eigenvalues are positive, right? So we can write A star A, we can find a unitary W such that A star A is like a diagonal matrix and then W times the diagonal times W star. Here, A star is an N by M, and A is M by N, so we have an N by N matrix. Okay, so W is an N by N. This diagonal matrix is an N by N. This is an N by N. Okay, and write this matrix as D squared. So the eigenvalues of A star A are just the square of the singular values. So let D be the matrix whose non-zero diagonal entries are all the singular values followed by zeros. So D squared is this matrix, or sorry, yeah, D is just like sigma 1, sigma 2, down to sigma R, and then zeros. Okay, so A star A, we write it as W, D squared, W star, and we modify D a little bit. We just make a new matrix E. That's going to be like the singular values of A followed by all ones. Okay. Let's keep that there. Okay, so on the top left corner, E and D are the same, and in the bottom right, D has all zeros, but E has the identity matrix down here. And E is again an N by N matrix. Okay. And just out of nowhere, we define a new matrix B. We define it to be A times W times E inverse is this matrix. And our goal is that we want to show, why do we do this? Because we want to show that A equals W some matrix sigma times V star. Okay. Oh, sorry. No, we want to show it's V sigma W star. So now that means that's the same thing as saying AW equals V sigma. Okay. So that means we want to take, we want AW to be V sigma. Okay, so we want to write B in basically in terms of, let's see, what do we want to do? We want to show, so our goal should be to show that B times E equals V sigma. That is our goal. Okay, this is just scratch work on the side. Okay. But if we can write B times E is some unitary V times our original matrix sigma. When we get there, I'll remind you what that is. But yeah, we're trying to show some kind of factorization for B times E. Okay, so with that as our goal, we compute B star B. Now, B is AWE inverse. E is a real, is an n by n matrix with real entries. So it's like its conjugate transpose is just itself. So E inverse star is just E inverse. So when we do B star B, well, B star is just E inverse W star A star. This is B star, and then this is B. Now A star A is WD W star. So now A star A is WD W star. W star A star A W is therefore W star W D squared W star W. So W star W is identity and W star W is identity. So this reduces to D squared. This is D squared. And then, so we reduce to E inverse times D squared times E inverse. Now the inverse of E is just the matrix with 1 over sigma 1 all the way down to 1 over sigma r on the diagonal, followed by all 1s. And when we multiply by D, D is the matrix with sigma 1 down to sigma r on the diagonals, followed by all 0s. Okay, so when we multiply this matrix all out, the sigma, we get sigma 1 squared, divide by sigma 1, divide by sigma 1, we get 1. So we get 1s, all where the sigma 1 up to sigma r were, and then D, the last, the bottom right corner is all 0s, so that becomes all 0s. Okay, so this is, B star B is this block matrix, identity 0, 0, 0. Okay. But we can, that means like, that gives us very special knowledge about B, because there's another way to find out what is B star B. We write out B as in its first R columns and its last n minus R columns, and then to compute B star B, we just, so this is B star, and then this is B, and we do a block matrix multiplication. Okay, so we do B1 star B1, and then we do B1 star B2, goes here, B2 star B1 goes here, and B2 star B2 goes here. But B star B has this form. So that tells us that B1 star B1 equals the identity matrix, and B2 star B2 is the 0 matrix. Okay, the only matrix such that B2, like the only matrix where B2 star B2 equals 0 is the 0 matrix. Okay, so B2 equals 0, and then the fact that B1 star B1 equals the identity tells you that the columns of B1 are orthonormal. Okay, so that means, because of that, you can find a unitary matrix whose first r columns are coming from B1, and the last n minus r columns. Basically, you can use like Gram-Schmidt process or something to find this B prime. I guess you could even do something like householder matrices or whatever. Doesn't really matter. We just find a unitary matrix where the first r columns are coming from B1. Okay, so we'll call this, so yeah, this is going to be a matrix. We'll call it V. Okay, and now we want to see, again, we want to prove that BE has some relationship to V, basically. Okay, so first of all, B times E. Well, B was the matrix B1, comma B2. Oh, sorry. And B2 is 0, so B times E is just B1, 0, and then E is like sigma 1 down to sigma R followed by all 1s. Okay, if you multiply this out, it just has the effect that each column of B1 is multiplied by a singular value, its corresponding singular value, and then this identity matrix gets multiplied by the zeros, so the rest of the columns are 0. If you compare that, that's the same thing that you get if you take the matrix D, which is sigma 1 down to sigma R, singular values on the diagonal followed by zeros, and multiply it by the matrix B1 B prime, because B1 times this part gives you this, and B prime times all zeros gives you this, same thing. All right. And then we call this V, we call this D, and we've shown that B times E equals VD, and B is just a matrix AW E inverse. So that tells us that AW E inverse E is VD. And then if you rearrange, so E inverse E is just the identity. And then if you multiply by W star, you see A equals VD W star. And what's this matrix W star? Or sorry, what's the matrix D? It's this matrix. Okay. And that's it. Okay. Now I just wanted to explain how, like, some useful things about the singular value decomposition. So first of all, we call the factorization you get V sigma W star. It's called the singular value decomposition. And something nice about it is that if you call if you look at the first R columns of V and the first R columns of W, you get you can write A as sigma 1 times V1 W1 star, sigma 2 times V2 W2 star, all the way down to sigma R times VR WR star. Right. And so what happens is that like the entries involved in each of these terms are basically like not too big and not too small in some sense. Okay. So the behavior of A is really determined by, these singular values. So like pretend, like what can happen is that like the biggest singular value or the biggest 5 singular values might be large, and then the rest might kind of decay and be really small. And then we can kind of approximate A by looking at like the biggest singular values. And I think there's many interesting examples of this, but I just wanted to give you kind of not a real example, but just kind of to maybe spark your imagination. So this is my completely fictional, useless example. Okay, let's pretend that we want to figure out something about tree frogs, and we somehow are able to find the following data for 30 tree frogs, like the length of their legs, their weight, and by some magic we're able to compute like how high they can jump, whatever. Okay, and we want to figure out like what's going on with these tree frogs. I'm sure you can probably think of a better example than this, but I don't know. Okay, and then let's pretend that so we have 30 tree frogs with three points of data for each. So we put it in a matrix. We have a 30 by 3 matrix. Okay, and then we compute the singular value decomposition of our matrix A. So our matrix A is a 30 by 3 matrix. Okay, so we're gonna have the minimum of 30 and 3 is 3, so we're gonna have 3 singular values. Okay, and let's just pretend like when we do it, the biggest singular value is 30, sigma 2 is 2, and sigma 3 is like 0.1. Okay, so v1, v2, v3, these are 3 of the columns of my unitary matrix V. W1, W2, W3, these are, well, W is a 3 by 3 matrix, so these are the so W1 is a 3 by 1 vector. Same for W2 and W3. So W is a 3 by 3 unitary. Actually, since A has presumably real entries, V and W are both have real entries as well. Okay, and we have the singular value decomposition. So, and what these singular values tell us is that, first of all, this is 0.1. We can kind of consider that to be like noise. Okay, so we can kind of ignore that. And then we have like 2 main terms. We have, I mean, this is just like a rough, very rough explanation, but we have 2 main terms. Okay. If we look at this matrix and we write the entries of V1, if we write V1 as V11, V21, all the way down to V31, and we write W1 is W11, W21, W31, then this says that the Aij entry of A is like 30 times V VI1 times WI1. Okay. Oh yeah, and this is approximately. Okay, that's just, we just focus on like this highest singular value. Right, it tells us that there's like some kind of, so remember W11, sorry, this should be AI. Oh, this should be a J. Sorry. Okay, yes, this makes more sense. Okay, so if we, what does this tell us? Right, Aij is like one of the 3 data points for the ith frog. So AI1, that's the leg length. AI2, that's the weight. And AI3, that's the height it can jump. And it tells us that all of those 3 data points depend on like some kind of hidden variable, VI1. Okay. And then we have to multiply by like some weight and also the number 30, you know. So it means like there's some uh, hidden interference which from which which determines the leg length, the weight, and the max jump height. Okay, I mean this is a completely fictional example, but I just wanted to give you an idea about how the factorization of this matrix can tell you useful things. Okay, and then we didn't talk about this too. It just means like there's like some secondary variable which doesn't affect things as much as this major term, but you know there's like some other variation coming from v2. Okay, so we could put plus error or like some kind of some more variation, you know. Okay, so you know, of course, you know, to actually use to actually apply the singular value decomposition, you not only need to have knowledge of linear algebra but also knowledge of your subject, so you don't go around saying completely useless stuff. But anyways, let's just stop there. Thank you.